So what is a chemical reaction? I'm sure you've heard of a chemical reaction before. Chemical reactions a lot of times are taught and you go into the details a little bit too much and then you kind of lose track of the whole point. And so the point of this video is to shine some light on a good foundation for you to have whenever you're thinking about a chemical reaction. And so no matter what level you're studying at, even if you're in graduate school taking chemistry and you're doing chemical reactions and stuff like that, clearly you probably don't need this video, but it's good to think back and organize your knowledge. There's a lot of people that have a lot of knowledge about the world, but it's not really organized in a way that is teachable to others. And so this is a nice way to kind of organize everything about reactions. So first off, chemical reactions in general, it involves a chemical change. So you had atoms and molecules to begin with, let's say, those are called the reactants. And then you have bonds, which are pretty much associated with the electrons. You have different kinds of bonds that I discussed in a different video. But bottom line is, you have these bonds that are rearranging themselves, and there's clearly some things that are new that are being produced that were not there to begin with. And so we have reactants coming together, or even if you only have one reactant, bottom line is you have something to start with, and then you have something at the end to finish. And those are called the products. Those are being produced. And so we're producing new substances. But in the process, we're not gaining or losing any atoms. And so if you count up all of the atoms of those elements on the left side and the atoms of the elements on the right side, it should be equal. And that's called balancing a chemical equation. And so we have these molar coefficients. And so this is just a generic chemical equation right here. We have reactant A and reactant B producing product C and product D. And you can insert whatever atoms and molecules you want, and we will later on with some examples. But bottom line is you have a certain amount of this stuff reacting to produce a certain amount of products, and we got to make sure that everything checks out in terms of the mass. It's called the conservation of mass. The mass of those atoms wasn't really created or destroyed. It was just those atoms just rearranged themselves, and they're bonding with different things now. There's new bonds formed, and there's bonds that were broken. That brings us to the next thing, energy. When you think about energy, think about when bonds break, energy is needed, and when bonds form, energy is released. One way I remember this is I think about, why do bonds really want to form in the first place? Well, usually it's to become more stable. So are you more stable at a spa or at a party? So if you have less energy, usually you're more stable. And so what happens when you're forming bonds is you're trying to become more stable by releasing energy to be at a lower energy. And so that's how I remember that bonds forming are releasing energy, and bonds breaking are absorbing energy. And so if you have a net release or a net absorption of energy, we call the reaction exothermic, if you're releasing energy overall at the end of that reaction. And if you're absorbing energy overall, then we call that endothermic. And this is really just describing enthalpy. And so enthalpy is looking at the energy changes in a reaction. And that really describes why a lot of reactions happen in the first place. The other thing that you got to look at, though, is entropy. It's those two E words. Entropy has to do with disorder. And so the enthalpy looks at the energy. The entropy looks at the chaos, the randomness. And so if your reaction is producing a whole bunch of randomness, then that's going to be favored as well. And so you got to look at those two things, and then you can get to something called Gibbs free energy, which pretty much tells you if it's spontaneous or not spontaneous. Bottom line is, that's one thing we can look at. We can look at the energy, and we can also look at the entropy. Right? Entropy. All right, and that's pretty much enthalpy and entropy. All right, and then the mechanisms. How is this reaction happening in the first place? Well, there's got to be some mechanism by which the reaction happens, and a lot of times we're trying to figure that mechanism out. And a lot of times, we come up with a mechanism, and then we come up with a different mechanism, and we're comparing which mechanism makes more sense. Bottom line is, a lot of that, especially with organic chemistry, which is a lot of the world around us, because carbon is the backbone for a lot of different stuff. And so carbon chemistry is pretty much organic chemistry. We're looking at nucleophiles, which is a negative part, attacking a electrophile, which is a positive part. And so that explains a lot of organic chemistry right there. And then the other thing you can talk about is a group that's leaving, so a leaving group of a molecule. You could talk about functional groups and how they function and what they do and how they make certain molecules similar, like ethanol versus methanol. They're both alcohols, right? They both have this OH group. And so a lot of times we're trying to figure out what the mechanism is by which that reaction happened, looking at the different steps that were involved. All right. Now, another thing is equilibrium and rate. So how fast is the reaction happening? If we timed it, how fast? And can we change the rate? Can we change it? Well, yeah, we could. We could increase the concentration, maybe. We could increase the temperature. We could add a catalyst. We could stir it. There's a lot of different things that we could do. If it's gases, we can mess around with the pressure. And this is pretty much Le Chatelier's principle is saying how we can kind of shift that equilibrium a little bit. And if you have a stress on the system, it's going to shift in a direction to relieve that stress. So that's a big part of chemistry right there, is equilibrium and rate. And so what do I mean by equilibrium? Well, chemical equilibrium is pretty much when you have something happening in one way and you have something happening in the other way, and they're happening at the same rate. And so let's say A and B are reacting to form C and D, but C and D, once they're formed, are going to be able to potentially reverse, because a lot of reactions are reversible. And the products are going to come together to form reactants, and that's just going to keep going until the rate of the forward reaction equals the rate of the reverse reaction, and then you're at equilibrium. And we have rate laws and rate constants and equilibrium constants and all sorts of stuff like that, and that has to do with equilibrium and rate of a reaction. Alrighty, and then the last major thing is stoichiometry and this idea of a limiting reactant. So stoichiometry pretty much is, do you have the right ratio? With your engine cylinders, you have fuel, right? You have gasoline that's combusting with oxygen. If you have too much fuel, that's a problem. If you have too much oxygen, that's a problem. We're trying to get the right ratio. And so bottom line is, if you look at the molar coefficients, A, B, C, D, we want those to match nicely. So let's say you're trying to make a grilled cheese sandwich with one piece of cheese. Well, you're going to need 2 pieces of bread, and you're going to need 1 piece of cheese. That makes 1 sandwich. But if you have 3 pieces of bread and 1 piece of cheese, then yeah, you're going to be able to make a sandwich, but you're going to have leftovers. And so this idea of having leftovers and getting the right ratio in order to produce what you're trying to produce, it's really starts to become practical, because now we can do some math, right? So stoichiometry type calculations involve, hey, I started with 15 grams of A, how many grams of D am I going to produce? Those are useful calculations for a reaction. And so that is really the last thing I wanted to talk about, just generically with this idea of a reaction. All right, now we're going to talk about the types of reactions, because clearly we can start classifying, because there's so many different reactions in the world. Anytime something changes or something new is produced, which is happening all around us, it's happening right now as I inhale and exhale, right? Biochemical reactions are happening in my body right now. Reactions are happening everywhere. So we have to have a way to try to classify it. All right, so what we do is we say, if you're producing something that is more complex, if you're creating something, synthesizing something, it's called a synthesis reaction. In organic chemistry, a lot of times we call that addition reaction, because you're adding something. What about combination? You could probably call it that too. I think I've heard people call it that. You're combining things. Bottom line is, you have, the way I like to explain it is, you have Abby and Bobby. And Abby and Bobby come together. They were single to begin with, and they're forming an Abby-Bobby relationship. All right, an easy example would be the synthesis of lithium bromide. In other words, you have lithium. Now these numbers in front are the molar coefficients, and so there's actually an invisible 1 here, right? And so these numbers right here are just telling you how much, right? And so bottom line is you have lithium coming together with bromine to produce lithium bromide, which is something more complicated. You had two things, right, coming together to form one thing. And so that's called a synthesis. Next is we have decomposition. Decomposition is, let's say you have Abby-Bobby together, right? They're in their relationship, and now they're breaking up. They've been together for long enough to realize they're not stable, and so they'd rather be apart. Those bonds break, and now you're left with Abby and Bobby on their own. And so a lot of times in organic chemistry, we call this elimination, which would be like your E1 and E2 reactions. But the general idea is you start with something that is together, and you're breaking it into its parts. You're decomposing it. So an easy example, open up your medicine cabinet, you'll probably find some hydrogen peroxide. Hydrogen peroxide, a lot of times on the label, it'll also say that it's stabilized, because hydrogen peroxide is inherently like unstable, right? And so this instability here, it's going to break down into water and oxygen all on its own. And so what happens is you started with something and it decomposed, and now this you only have one reactant, and it's decomposing into, let's say, 2 or 3 products at the end. So that's the general idea with decomposition. All right. Single displacement and double displacement involve swapping, like displacing or replacing. You could also say substitution, like your SN1, SN2. Notice how we start with 2 products and 2 reactants, right? So there's 2 reactants on the left, and there's 2 products on the right. Bottom line is the first one is a little bit depressing in terms of our story here. We got Abby and Bobby are together, and Chase is lurking in the background. And Chase comes along, Abby and Chase end up in a relationship, Bobby ends up on his own. So a little bit upsetting for Bobby. But a good example of that would be like potassium coming together with silver chloride, and then potassium is kind of like Chase comes along, takes the place of Bobby, which was the silver. Bobby, the silver, is left on his own at the end. And so you had a single displacement there. The other thing that you could talk about is a double displacement. So this is a little bit happier. Imagine you had 2 partners together to begin with. So Abby and Bobby are together, great, and you have Chase and Danielle are together. And in the process, they're just going to switch partners. And so Abby is going to swap and they're going to be ending up with Chase. Bobby ends up with Danielle. Everybody's happy at the end. So an easy example of this would be magnesium chloride coming together with potassium hydroxide. And so the hydroxide part that was originally with the potassium metal is going to end up with the magnesium metal instead now. And then the chloride part, which was originally with the magnesium, is going to end up with the potassium. And so pretty much the metal and non-metal parts are switching. Awesome. So that is it for your general types of nice reactions that we can kind of put easy A, B, C, D labels on. Over here it gets a little bit more specific, and now we're into our other types. And so the first type that I would say is probably the most important that we talk about is combustion. And so combustion involves a fuel having carbon, hydrogen, and oxygen. It's not all the time oxygen, but sometimes. And so you can have something like methane gas, which does not have the oxygen, or you can have like an alcohol, which would have that oxygen. And that's going to react with oxygen to produce carbon dioxide and water. So many fuels are reacting with oxygen to produce the same products. That's really amazing. So like gasoline, methane, ethane, propane, butane, octane. We got ethanol, methanol, propanol, butanol, whatever. All right, all of those fuels are reacting with oxygen from the air most of the time, right? And that's going to produce carbon dioxide and water. It obviously is going to happen with different amounts, and that's why I have the A, B, C, D here, because the molar coefficients are going to change. But the X, Y, Z, how much carbon, how much hydrogen, how much oxygen are you going to have reacting with that fuel, that's going to change too. But bottom line is our example would be methane reacting with oxygen to produce carbon dioxide and water. So the other thing to think about, which a lot of people don't with combustion, is think about biology, the study of life. Think about how this relates to biology. Well, cellular respiration, which is pretty much happening with all of your cells, right? Your cells are taking in oxygen that you're breathing, and they're taking in fuel, like let's say glucose, sugar. And they're reacting that to produce carbon dioxide and water, and when we exhale, we get rid of that carbon dioxide that our body produced. So that's a really, really important biological reaction, isn't it? So that is cellular respiration. The other opposite form of that, right, would be what happens with plants, and that's photosynthesis. And so isn't that just the opposite? So if we take the carbon dioxide from the air and the water from the ground, let's say, from the plants, right, and they can turn it back into oxygen for us and sugar. So pretty cool that we can look at combustion and actually relate that to cellular respiration and photosynthesis. Pretty awesome. Which I would say are really the two huge bioreactions that we can talk about. All right, now number 2, acid-base. So this is really just kind of like a double displacement reaction, but it's a very specific thing. Acids and bases are important. We have this pH scale that tells us that. The lower pHs are the acids. The ones that are less than 7, the ones that are greater than 7 are the bases, and when they come together, they neutralize each other. So you could call this an acid-base neutralization reaction. Bottom line is you have an acid and a base producing a salt and water. So a good example would be like the gastric acid in your stomach, like hydrochloric acid. So hydrogen chloride gas dissolved in water, it produces hydrochloric acid, very common acid. Is reacting with NaOH, which is a very common base. It's sodium hydroxide. And so notice how the H part is really what makes that an acid, and the OH part is kind of what makes it a base. And so you recognize that it's an acid reacting with a base, and we know that that's going to produce a salt, which is NaCl. Well, that's just table salt. That's easy to recognize, sodium chloride. And then we have the water is being produced, which that kind of makes sense why it's neutralized. It's producing water, which is neutral. So the acids and bases came together and they neutralized each other. Awesome. So now the third type, which is really important, is redox reactions. And so we have a reduction and an oxidation happening. What does that mean? Well, generally it's described like this. Leo the lion says grr. That's one way to remember it. Bottom line is, if something's losing electrons, it's becoming oxidized. And if something's gaining electrons, it's becoming reduced. And so you can see how once this electron is transferred over, the A just lost the electron, so it's becoming oxidized, and the B just gained the electron, so it's becoming reduced. And so that explains a lot of reactions. It pretty much, it's one way that ionic bonds can come about, right? Because we know that ionic bonds are the attraction between ions. And so when sodium loses an electron to chlorine, and it produces that ionic bond like sodium chloride, so ionic bonding can kind of be explained by this idea of a redox reaction. You also look at electrolysis, which is pretty much sending electricity through water and splitting it into hydrogen and oxygen gas, which is awesome. A lot of stuff with electricity, batteries, stuff like that. A lot of that can be explained like anode and cathode and stuff like that. That a lot of times can be explained by a redox reaction. Okay, so redox reactions, super important too. Number 4, hydration and dehydration. It's just like what it sounds like. Hydration, if you hear the word hydration, you're probably gaining water. You're hydrated, right? And dehydrated or dehydration reactions, right, they're going to be losing water. And then you have these Maillard and caramelization. Those are kind of like your food reactions. And so the Maillard reactions are between amino acids, which are like the building blocks of proteins, right, and sugars. And so sugars and amino acids are browning. It results in browning. And same thing with caramelization for sugar. And you have this browning effect that you'll see in a lot of meats, and you'll see it like because meat has a lot of protein in it, right, which is made from amino acids, and then you'll see it with sugar. When you heat it up, you all know what caramel looks like, and so you heat up sugar and it starts to caramelize. And different sugars are going to caramelize a little differently, but because remember, sugars are pretty much carbohydrates, and you can have monosaccharides, disaccharides, polysaccharides, and you have the different classification of carbohydrates, but bottom line is sugars in general usually caramelize when you heat them. All right. And you also have reducing sugars here. So reducing sugars, all monosaccharides are reducing sugars. Just a little bit of info for you. Bottom line is that is our fifth one for our other types, and then the last one would be precipitation, which is where you a lot of times have an aqueous solution of one thing and another thing, and they're reacting together to form a solid. And so one lab that I do is I call it the Liberation of Sulfur. And so we take sodium thiosulfate, and we take the sulfur and we eventually get it to precipitate out, and we have a yellow solid that collects. It's really cool. So I would say in general there's probably more. I'm probably missing something, but I think that this is a pretty comprehensive list on what you're going to deal with, and it gives you a place where you can have a nice foundation of everything involving a chemical reaction with all of those concepts over here, and then the classifications over here. And so remember, there's 4 general types, but then there's some pretty important specific types that I'm sure you've heard of and will hear of again. So hopefully that helps, and hopefully that gives you a good foundation on what a chemical reaction is all about. And you can see right here is a very, very important mistake, and I need to add an A. Caramelization. Some people spell it with an S too, because spelling is super important.
So one specific example that we could look at is if we had a reaction between magnesium and oxygen, magnesium being a solid metal and oxygen being a gas from the air. And so if we had a reaction between those two, what would we produce? Well, we would produce some sort of a magnesium oxide, and we want to figure out the identity of that. And so one way to do that, we'll put some X and Y subscripts here representing how much, what is the ratio, what is the identity of this product. And we're going to see if we can figure this out experimentally. So we're going to produce some sort of a solid product. We want to figure out what it is.
So we take some magnesium metal ribbon right here, and it's tarnished a little bit, so we need to sand it with some sandpaper real quick. And so after we're done sanding it, it looks a lot shinier. We can get rid of most of the contamination on the surface, and we're pretty much left with more of a purified magnesium to start with. And then what we can do is show you what this reaction would look like just on its own. So we got some magnesium, and we're going to heat it up, and it'll hopefully react with the oxygen that's in the air. And so we'll just heat that magnesium up, and it's going to be absorbing that oxygen from the air, and it starts to get super bright, and that magnesium is releasing that white powder, turning into, you see all that white smoke, magnesium oxide. And so that's pretty much just a powder at this point. And so we just produced magnesium oxide. But how can we do that in a controlled environment? So in more of a controlled environment, we can take some mass measurements here. And so we can figure out how much it weighs, how much we start with in terms of magnesium, and then we can put it in here, heat it up. It's not hot right now, but this was already done. You can heat this up, and we can do what you just saw in a controlled environment. We can capture all of that, and notice how it's some on the lid as well. And then pretty much if we know the mass of the container, then we can figure out what the mass of the end product is, and we can try to figure out, based on just the masses really and the difference in mass before and after, we can figure out what happened. And so that's what we'll do real quick as a real life example.
All right, so let's assume that we know what we start with, right? And so I've done this a bunch of times. I just did it again. These are the numbers I got. I always get numbers that are pretty similar. My students are also getting numbers, as long as they're pretty careful. They get numbers that are pretty similar to this, so we can kind of be confident with this data. And so we start off with 0.170 grams on the scale. That's what I just got. And at the end, when I weighed it, after the reaction, this magnesium oxide that we produced, whatever that product was in there afterwards. Now remember that we dried it too. I made sure to get rid of all the water weight before and after, minimize contamination, all that good stuff. But if you're thorough about it, you should be able to get something along these lines here. So 0.280 grams is what I measured afterwards. Nice round numbers for you in terms of that third digit, which was nice. And so the question is, how much oxygen did we use? Well, if you think about it, it must have just been 0.11. So if we started off with 0.17, we must have absorbed 0.11 from the air. And so the scale was not reading the oxygen initially. But you can think about it like the magnesium is kind of sucking up that oxygen and absorbing that oxygen from the air when it's reacting. And so it's actually gaining mass. And so the gain in mass here, which is 0.11, is associated with that gain of oxygen, the element oxygen. Now we know it exists as O2 in the air, but for now we don't really care about that. For now we just are looking at the element weight. And on the periodic table we see that the molar mass of these substances can be found just looking at the periodic table. And so if you take the mass in grams divided by the molar mass, you're going to be able to get the moles. How many moles do you have? And so we figured out the moles of each of those elements. And we look at these and we say, okay, well, I'm trying to figure out X and Y, like what is the identity of my product? And all you have to do is look at these numbers and divide each number. We want the ratio of these two elements in this compound. So we're going to divide each of these numbers by the smallest one. And when you do that, well, the smaller one is the 0.0068754. Okay, so we're going to divide both of them by that. Well, when we divide this by itself, we're just going to get 1. But when we divide this by that, we're going to get something a little bit greater than 1. But very close to 1. And so this points out that, hey, we probably have a 1-to-1 ratio of magnesium and oxygen, or we could write it as MgO. So we just kind of identified our product there. And now we can look up the molar mass or calculate it just by pretty much adding these two together. And we can get our molar mass now, because there's one of each, of our product, and we pretty much are able to say, okay, well, this is how much, by dividing those two, how many moles I produced. So that's the general idea about how you go about something like this. The next thing we could do is do a little research, and we know that magnesium oxide, the chemical formula is MgO if you do the research, and that's well accepted in the scientific community. And you also can research a little bit more, and we know that it's a supplement used to treat or prevent low levels of magnesium in your blood. And so in your blood you do have metals floating around. You got electrolytes, but you also have, like, iron, for example, is on your hemoglobin. It's really, really important for carrying oxygen in your body. But magnesium is pretty important for your body too. So if you're low on magnesium, then you can take a magnesium supplement. So you might see it in more of a pill or supplement form, but you might as well, look at it like the white powder, because that's kind of what we saw when we reacted it. And if you look at the theory, it also really makes sense that it would just be 1-to-1 ratio, because magnesium has 2 valence electrons. It tends to have 2 valence electrons because it's in group 2 of the periodic table. It's an alkaline earth metal. And so when you combine that with oxygen, which has 6, then, well, oxygen needs 2 more. And so magnesium is just going to donate, and oxygen is going to accept, and you're going to create magnesium oxide, which is pretty much a redox reaction, right? I mean, you're transferring electrons over there. Something's being oxidized, something's being reduced. or changing the oxidation numbers. And the magnesium is going to have it's going to be a 2 plus ion, and then we're going to have a negative 2 charge on that oxygen, and they're going to be attracted. Positive attracts negative, and it's a nice 1-to-1 ratio. The other thing you could ask is, how much did we produce relative to maybe what we should have produced theoretically? Well, we know we produced 0.280 grams. That's what I weighed after the reaction. But we don't quite know how much I created theoretically. And so what you could do is take a look at the reaction. So we know that the magnesium reacted with O2 from the air. And most of the air is a diatomic oxygen. So about 20% of that air is diatomic oxygen, and pretty much the other 80% is diatomic nitrogen. And you have other gases in the air too, but bottom line is we're pretty much looking at the identity of the oxygen in the air as O2, reacting with magnesium to produce this MgO that we just said, but that's not balanced. So we just talked about this a little bit before, how we need to have the same number of atoms on both sides. Right now I have 2 atoms of oxygen on the left and 1 of magnesium. Over here I have 1 and 1, so that's not balanced. So what I need to do is change these coefficients in front. The 1 is a lot of times not shown, but I'll show it here. And so now we have 2 magnesiums on the left, 2 magnesiums on the right. We got 2 oxygens on the left, 1 oxygen molecule, meaning 2 oxygen atoms, and then you got the 2 magnesium oxides, so you got the 2 oxygens over here now too. So awesome how we can change these molar coefficients. Now we have a balanced chemical equation, and we can do some stoichiometry. So you got to ask yourself, theoretically, how much should I have produced? Well, I started with 0.17 grams of magnesium. Now you can put that over 1 if you want, no big deal. And then you can say, okay, well, I'm going to convert that to moles, and I'm going to divide it. And I already did this earlier, and we divided it by the 24.305, and we get how many moles of magnesium we have. And so we just divide by the molar mass pretty much. Then we can convert the moles of magnesium to moles of magnesium oxide. Notice how the units are canceling as we go. And so this balanced chemical equation says that for every 2 moles of magnesium, I'm going to produce 2 moles of magnesium oxide. So it's pretty much a 1-to-1 ratio. 2 over 2 is just 1. And so that works out nicely. It just converts itself nicely. The units convert, but nothing really happens with the number. We keep going, and now we want to figure out how many grams theoretically of magnesium oxide we should have produced. So we know how many moles we have, and so we just got to multiply by the molar mass, which is 40.304, and we're finally left with about 0.282 grams theoretically, which is really, really close. I was pretty surprised by this result. And so we plug this newfound knowledge into our percent yield for our theoretical value. And so we get 0.282, we divide that, we multiply by 100%, we get 99.3% yield, which is great. The closer you are to 100, usually the better. That means that your experiment really lines up with your theory. Now there could be problems with your theory, and there could be problems with your experiment. A lot of times in the lab things can go wrong. For example, when I did this experiment, some of the white smoke of that magnesium oxide as it was being produced escaped a little bit, so we lost a little bit of mass. You got to make sure things are dry before and after, otherwise you got water weight affecting your experiment. Maybe you didn't completely react. So a couple of my students, they thought that they were done with the reaction, but I put the flame over it again, and the reaction continued. So they didn't actually go to completion. Like, there was still some magnesium that was unreacted, so we had to heat that up and react it. There's a lot of different things that could have gone wrong, but in general, ideally, you're going to be pretty close to 100. Usually my students get somewhere between 85% yield and 115% yield. There's reasons for you producing more than what you expected, and there's reasons for you producing less than what you expected. But that's how you work with your percent yield. And so far we've been talking about the synthesis of magnesium oxide, but you can also continue this discussion to iron. Iron can react with oxygen to make iron oxide. You see this is pretty much rust. And that's actually gaining mass, just like we talked about with the magnesium. So when things rust, it's actually absorbing, that iron is absorbing oxygen from the air. And A lot of times you think about rust as losing mass because things that rust tend to kind of fall apart, and you associate that with losing mass. But in reality, things that are rusty are heavier. They absorb that oxygen from the air. So that's pretty interesting. And it's also a 2 to 3 ratio that's a little bit different than the 1 to 1 ratio that we saw. If we look at this 1 to 1 ratio, this is with zinc though. And so zinc can also react with oxygen to create zinc oxide. Now copper is pretty cool, and other elements are interesting like this too, where multiple things can happen and it can still be stable. So copper, you can have copper 2 oxide or copper 1 oxide, take your pick. They're both pretty stable. Copper 2 oxide is just going to be a 1 to 1 ratio, and then the copper 1 oxide is going to be a 2 to 1 ratio. And so it just is a question of how much that copper wants to, how much oxygen it wants to absorb. So as you think about what we've gone through, try to relate that to all of the reactions, and just try to understand that with every reaction you're going to follow some sort of a similar line of thinking to what we just went through. And hopefully I showed you the importance of some of the details like stoichiometry and this idea of producing something new and identifying the product and percent yield and all these things that chemists do all the time. And so hopefully this video helps and shines some light on chemical reactions. We'll see you next time.